So hi Margaret, I did a little bit more equilibrium for you. We should talk tonight. It's Tuesday morning now, but we should talk tonight and you could let me know what you're doing in class so I could do the type of problems you're probably getting to now. So this might be a little bit behind, but I thought I would do it anyway. So if you saw my last video, it should seem pretty easy to calculate equilibrium constants. Remember, sometimes we call it Kc when we're using concentrations, sometimes just K. But when you have all the concentrations of everything at equilibrium, it's really easy. So here's a problem where you have 2 SO2 gas plus 1 O2 gas going to 2 SO3 gas. At equilibrium, if you're given these three numbers, you simply have to plug them into the right spots. Don't forget to raise them to the proper power, and then report the Kc. One little thing, even though these are written as concentrations in terms of moles per liter, the final answer does not have any units. So in this one, I calculated a K value of 1.28 times 10 to the fourth. That's a pretty large value. That's, 12,800. When you have a large K value, that means that the reaction is so-called product favored. Now, more commonly, you'll only be given initial concentrations and need to do more involved calculations. So here's the same reaction. Suppose you were told that 0.0010 moles of each reactant was placed into a 1 liter flask, and then after you reach equilibrium, 0.00054 moles of SO3 have been formed. In order to calculate the equilibrium constant, you need an ICE table, because you need to fill in the blanks basically. So look what I've done here. I've used blue to indicate that this is the information that I have. I have 0.0010 molar SO2, and I simply got that by taking the moles that I was given and I divided by the volume, which in this case was easy because it was 1 liter. So the initial amount of SO2 and the initial amount of O2 are written in the proper spaces. There is no SO3 when you start this reaction. The key thing to do is to look at the stoichiometry, so that whatever amount reacts, you need to indicate that for each reaction as written, you're losing 2 SO2s for every 1 O2. And the way we do that is we'll just write minus X for the chemical that just has a 1 as a coefficient, and minus 2X for the chemical that has a 2. So that means the equilibrium line is the combination of the two lines above, so I have 0.0010 minus 2X in this slot, and I have 0.0010 minus X in this slot. Because the product creates 2 SO3 molecules for each reaction event, I make 2X. That's the change. Because, again, we're basing this on saying that X corresponds to anything that has a 1 coefficient. Well, this actually ends up being pretty straightforward because of the initial information. They told us that the final concentration of SO3 was 0.0054, and we know that that line is the same as the sum of the two lines above it. If you just add a 0 to 2x, you could solve for x. Very straightforward. And I got my calculator here. 0.00054 divided by 2 is 0.00027. That is really useful, because now I could use that x and plug into the situations above. And so now I could calculate my Kc with all the elements put in. So I'm going to put the concentration of SO3, which was 0.00054, squared is the numerator, and the denominator is going to be the 0.0010 minus 2 times x times 0.0010 minus the x, 0.00027. Whoops, I forgot my squared. This is a pretty ugly calculation here. I probably could have saved some writing by actually solving for the subtraction. This happens to be 0.00046. And then this one is going to be 0.00073. Okay? So when I solve for Kc, I get, I'm going to need some time on my calculator here, so I square that and I divide by 3. I got a big number. Let's see if I got the same number that's in my book. I got 1888. I only really had 2 sig figs here, so I probably should write it as 1.9 times 10 to the third. Okay. Let's take a look at another one. Calculate the K for this reaction. This is a redox reaction, you could see, because you have different charges changing. So for this redox reaction, if the initial concentration of the iron 3 plus is 0.200 molar, and the I minus is 0.300 molar, and the final equilibrium concentration is 0.0866, you can see I've taken the ICE table and structured it with the given information in black. Now again, keeping in mind that I'm starting with 0 products and that the change line is all based on the idea of using X as any chemical that just has 1 as a coefficient. I don't have any of those here, but I could still use that as the basis. Oh, I'm sorry, the I3 minus has a 1 in front of it, so we're good there. Okay? So, what this is telling me is that the final concentration is exactly what X is, 0.0866. So my equilibrium line, 0.200 minus 2x, I'm going to plug this in and see what I get. 2 times 0.0866. So that's 0.0268 for the iron 3 plus. And for the I minus, it's going to be 0.300 minus 3x. 0.0866. Usually give your calculator a real workout on these types of problems. 0.0402. And then I have 2x in the final slot that doesn't have any numbers. This is just 2x. So this is 0.1732. All right, so my goal is to calculate the K, and the Kc for this reaction is going to be the iron 2 plus squared times the I3 minus raised to the first over the iron 3 plus squared times I minus raised to the third. So now I get to plug all my numbers in. So I have the 0.1732 squared times 0.0866 over 0.0268 raised to the second times 0.0402 raised to the third. And I've got several numbers to multiply and divide on my calculator. And I get a big number. For this one, I get 5.6 times 10 to the fourth. So, I got a last one that you could do and then get back to me. So now you try. For this reaction, a solution is prepared by dissolving 0.0500 moles of this chemical in a solvent. The total volume is 2.5 liters of solution. When the solution comes to equilibrium, the final I2 concentration is 0.0035 moles per liter. So I twisted it up for you a little bit because I gave you the initial moles over a different liters. I want you to calculate the Kc and determine the final concentration of all the components. So hopefully you can do that on your own. Get back to me tonight and we could talk a little bit more about what you're doing in chem. All right, take it easy. Bye.